Today I'm going to try something new. If you've been watching some of my videos recently, you'll sort of figure out quickly that this is sort of where a few of my previous videos start to come together. In the back is a Zenith radio from the 1930s. I think it's a 5S 319. At any rate, it doesn't really matter. It's basically a pre-war Zenith AM shortwave radio. This particular model, by the way, I'll just mention, I saw in a video that Edward R. Murrow did after the war from his apartment in New York City. And this radio was sitting on the shelf behind him. Now, other than that, I don't know anything about, not this particular radio, but a radio of this model was sitting on a shelf behind him. So I'm assuming that this is among the radios that Edward R. Murrow may have owned during World War II. But at any rate, that's one reason that I got this particular radio. After I saw that, I went out and found one. But that's not what this video is about. What this video is going to be about is the device that's sitting in front of it in conjunction with the radio. The device in front of it is the Syscomp SIG101 signature analyzer. And if you haven't watched my videos on the Syscomp, I suggest maybe you might want to go back there. I'll give a very brief review in a second, but basically you need to go back and look at those if you're not familiar with how signature analyzers work. What I'm going to be trying to do is to use a signature analyzer to test this radio. And I want to test it before I power it up in any way. Now, I know this radio sort of works, but I actually restored it about 15 or 18 years ago. And it worked then. But frankly, it's been sitting ever since, never been turned on. So what I want to do is go in and see if I can use a signature analyzer to test an old radio like this. Now, if I can't find anything wrong with this one, I've got a whole attic full of old radios. I'll find one eventually that has some problems and I'll be able to do it. So that's where I'm going. Using a signature analyzer to pre-test radios, particularly vintage radios, for bad components and things that maybe should be replaced before you ever power them on. Now, before I go into that part, I will caution everyone that these tests will be made with the power off. But if you're going to work on any electronic equipment with the power on, be sure that you understand the safety rules. Even these old radios can be dangerous, and certainly there are a lot more dangerous pieces of equipment out there. So if you don't know the proper safety rules, please don't do this. And finally, I suggest that if you're going to get into radios and you're a beginner, try to find an experienced mentor to help you out, maybe through a radio club, or look around sometimes local schools that have electronics programs. The instructor there might know someone. At any rate, get a mentor who understands the safety practices that are needed with old equipment like this. Okay, now of a brief review of the Syscomp. The way that this thing works is it tests components like this capacitor or this resistor. It tests the voltage current characteristics of those. So let me line up on the software and show you what I mean by that. Here you see a capacitor. One lead is connected to the ground lead of the input to the signature analyzer, and I'm going to be touching the other lead with this test probe. I thought I'd show you that so that when you see the software running, and this unit plugs into a USB jack of a computer, and then there's software on the computer that actually does the signature analysis. If you don't have one of these, I also showed in a previous video how you can use an Analog Discovery 2 to do the same thing. There are also a lot more models out there. So let's take a look at the software. Now I have the software running on the computer. This particular one is a Windows 7 computer, but I understand this software will run on practically anything from Windows XP up to Windows 10. You notice that I have capacitors selected there, and I'm now going to touch the capacitor, and you'll notice that there is a display in the center. Here is now I touch it, and you notice how you get a circle, and that is the current voltage characteristic, or the typical signature of a capacitor. So what I'm going to be doing with the Zenith radio is going through a series of test points looking for bad capacitors. And to do that, I'm going to have to first take it out of the case. So let me do that, and then I'll get back to you. So here is the Zenith radio out of its cabinet. This is a 5-tube superhet. I mentioned earlier it has 2 bands. This is the band switch. This is the tuning here. Of course, volume and I'm sorry, I think this is the tone control. And I think this over here is the band switch, if I remember right. It doesn't really matter for what we're going to be doing today. But what we're going to be doing is probing points in this radio before we ever try to power it up to see if there might be particularly bad capacitors. And I'm going to be doing it in a somewhat unique way. Normally, people work on these, including me, by turning them up on end like this and working underneath the chassis. I'm not going to be doing that. You may notice up here I actually have a new capacitor that I had put in. That capacitor must be at least 15 years old because I know I haven't touched this radio in that amount of time. But it still has in it some old paper capacitors, and if you watched my video on vintage electrolytics, one reason that I started thinking about that is I am pretty sure that it's a good idea to replace all these old paper capacitors. So I probably will do that in this unit before I put it back on the shelf. But I want to test them first to see just how bad they are. But in order to understand what I'm going to be doing, let me give you a look at the schematic. Here is the schematic of the radio, and I'll just point to the general. You don't need to be able to read this. I'll show you a blown up version of this in a minute. The power supply is down here with a rectifier. Then the speaker field coil is used as an inductor as part of a pi filter in the power supply. It has a 6A8 converter tube, a 6K7IF, a detector amplifier using a 6Q7, and then a 6K6 output tube for the loudspeaker. What we're going to be doing is we're going to be looking at things like this capacitor, for example. And like I say, I'll show you this in a little more detail in a second. This particular schematic comes out of the rider service manual for this radio. However, the rider service manual actually comes from Zenith's original factory. And here, for example, is one of their original, well, it's a reprint of one of their original service manuals. And this radio is in this particular volume. That's why I got it out. So you can find rider manuals online. You can also buy high-res versions on CD or DVD and so on. But at any rate, all of this information is pretty readily available online. There also is an alignment procedure, a parts layout, and then a voltage chart, which can be very useful. But of course, to test the voltages, you need to be able to power the unit up. We're going to try to test it before we power it up. This is a bigger version, or a blown up version, of a part of the schematic you just saw. You see here some capacitors that are actually electrolytic capacitors, C16 and C17, that are part of the power supply, you notice that they go from each end of the field coil to ground, which is this, I'm sorry, I'm telling you wrong, this is B plus here. The output is from the tube is connected there, and then the capacitor and the field coil are used to filter the AC ripple. But what we want to test is not these electrolytics, because I think there are better ways to do that than what I'm going to be showing you. What I want to do today is to see about capacitors like this, the plate bypass capacitors and grid coupling capacitors, or in this case, this is a bypass capacitor. But if a capacitor like this is leaky, the plate voltage from this plate will wind up on the grid of this tube, and that will cause this tube to conduct more than it should, and eventually it can ruin the tube. So one of the things you want to do is get rid of all the leaky capacitors. The other thing is, if one of these capacitors is leaky, then the B plus is shunted to ground. That puts a load on the rectifier tube, because the rectifier tube now has to supply more current than it was intended to. So those are the things we're going to be looking at, these capacitors and these capacitors, to see whether we can test them. Now, the nice thing about a signature analyzer is you can use it either with respect to ground, like across these capacitors, or right across this capacitor. Now, I'm not saying that it necessarily will show us what we want to find out. This is an experiment. But I'm trying to find out whether it will indicate the difference between a good capacitor and a bad one without us having to power the unit up. The way I'm going to be testing this radio instead of from the underside is by using socket adapters. Now, you can buy these on eBay. They used to be readily available. They're getting scarce, but if you are going to do much work on old radios, I suggest you get yourself a set of these, especially octal, and for newer radios, a set of 7 and 9 pin. I wish they made loctal adapters, and maybe they did, but I was not fortunate enough to ever find any of those. But I have a few of the octals that I use, and by the way, it's sometimes useful to have more than one, because you can plug in then for one tube, like you see at the base of this tube is this same kind of socket, and then you can put another tube in a socket and measure between the two. At any rate, that's what I'm going to be doing using the signature tracer. Now, the particular tube I'm going to start working on is the 6K6. That's the one that's set on the adapter here. And the 6K6, I've written the pin numbers. What I'm going to show you is first what a short looks like. And then we are going to go and look at the relevant pins, 3, 4, 5, and 8. Those are all of the pins that are actually active on the tube. Now, one thing I will point out that you'll find out pretty soon, there are going to sometimes be other pins on these tubes that are not used by the tube itself, but they are used in the wiring of the unit. In other words, they use a spare pin, like, for example, we show here 3, 4, 5. Here is 2, 7, and 8. So you might ask, well, where's pin 6? Well, pin 6 is not used on a 6K6. So pin 6 may be tied to anything and just used as a wiring point. So let's start with pin 7, and then we'll look at some of the others. I want to show you the screen as I do that, and I'll just call out what I'm touching at the time. Okay, now I'm set up, and I'm going to touch the probe to pin 7. You may recall that is shorted to ground, and that's what a short looks like. Now, I'm going to do pin 6 just to show you what pin 6 is apparently an open circuit. Now pin 5. And you see pretty much an open circuit there. That's the control grid. Pin 4. Okay, there you see we have a nice ellipse. So there must be a capacitor on pin 4. Pin 3, which once again is the plate. And you notice there is a capacitor there, but quite different. Pin 2, which is the other end of the filament. So that's basically shorted to ground. And now pin 1, which is basically open. And pin 8, which is the cathode. Okay, you notice that pin 8, and I think it's pin 4, have this distinctive ellipse. Now pin 3 has a little bit of an ellipse. So let's look at the schematic and see if that makes any sense. I've redrawn the schematic. The one that I have been showing up till now is the actual schematic produced by Zenith and reproduced by Ryder in their troubleshooting manuals. The reason I've redrawn it is to emphasize something. These resistors and the field coil, of course, when the field coil is in there for DC, these resistors become essentially out of the circuit. The DC resistance of this field coil is just a little over 2,000 ohms. So, of course, the 490K that across there is completely swamped by the 2,000 ohm DC resistance of this filter choke, or it's actually the speaker field. I have this unplugged right now. There's a plug on the back. So basically this is disconnected and this is disconnected. That's important when we look at the signatures and measure resistances in a minute. So the 6X5 is the rectifier. The center tap of the power transformer is tied to one side of a filter capacitor, and the other side, the positive side, is tied to the cathode. So as the plates alternately go positive relative to the cathode, current flows from the center tap through that capacitor and into the cathode and then to the plate, of course, charging this capacitor. Similarly, the current that flows through this capacitor, and of course with the field coil plugged in, or I should say with the speaker field plugged in, the current flows through it and through this capacitor also, charging it. And the purpose of this network, it's called a pi network, because if you look at it upside down, it looks like the letter pi, the Greek letter pi. By the way, you may ask, why did they use a 390 and a 100? Because 490K was not a common value, and this radio was produced in 1938. So they just used the two common values that were available, a 390K and a 100K. You could have used a 490 or a 500K here. So these are 8 microfarad capacitors. Usually in these tube circuits, they did not use big capacitors. And if you watched my section on vintage electrolytics, you'll know that one reason that they didn't use big capacitors is these were already big enough the way they were built in the day. They really were overbuilt. Big, thick aluminum, big, thick spacing, a lot of electrolyte. So they tended to use small capacitors. And they could get away with that because the speakers of the day had this nice inductor that they could utilize to help smooth out the ripple. Okay, so this produces a value of positive voltage here relative to this point. This you might call B minus or common. This you might call B+. Notice that B+ is bypassed to the chassis through a small 0.05 microfarad capacitor. We'll come back to that. Then B+ is connected through the output transformer primary to the plate of the 6K6. Its cathode is connected here, but notice that the cathode is also connected to chassis, which is this point, through an 80 ohm and a 150 ohm resistor. The 150 ohm resistor is shared with the 6Q7, which is the first audio amplifier, also the AVC tube, but we won't talk about that in this video. Basically, these are the audio amplifiers. This is the preamp. This is the amplifier. Now, I haven't shown the interconnections between these two, but what I am showing is the cathode of this one shares a resistor with the cathode of the 6K6. Similarly, the B+ is connected through a 220K resistor to the plate of the 6Q7. So, where I am going is I'm going to try to fill out this chart. For the 6K6 and the 6Q7, the plate, the screen, the control grid, the cathode. In the case of the 6Q7, the plate, the grid, which is the top cap, and the cathode. I'm going to do that by measuring resistance with respect to the chassis in this column. That's just using a multimeter. Capacitance with respect to the chassis in this column, same multimeter but on the capacitance setting. Then I'm going to take a signature of each of those pins using the SIG 101. Then I'm going to repeat the resistance measurements, but with reference to common, that is what I called B- a minute ago, not the chassis. Similarly, the capacitance and the signature. Now, I'm going to denote the signatures, I'm going to divide them into basically three classes. E up, that is ellipse with the major axis primarily up and down. E angled, which is about 45 degrees, and E flat, which is around 0 degrees. So that is the notation I'm going to use to fill in here, just because I don't want to have to try to draw pictures that are of each of these. I'm just going to write the letters EF, EA, and EU in each of these. Now, this video has gotten a little bit long, so what I'm going to actually do is postpone showing you the filled-in values. I haven't actually done them yet, but I'm going to do them next. But I'm not going to put that in this video. Part of the reason is I would like to introduce, frankly, a very old troubleshooting technique introduced, or at least published by John Ryder in 1932, called the resistance method, or servicing by radios by the resistance method. He published a book on this, and basically what he tried to show is how you can use an ohm meter to find many of the problems in the radios of the day. So his method is basically what I will be doing in this column and in this column, because he not only talks about resistance readings to the chassis, but also resistance readings between 2 points in the circuit. Because modern multimeters have capacitance scales, I'm going to put the capacitance in here, and there's a reason for that too, similarly over here. The reason I want to put the capacitance is, when you look at the signature, what you are looking at is actually the effect of the resistance and the capacitance taken together. And remember that that is going to vary with frequency. While the meter measures capacity, the signature analyzer is actually comparing capacitive reactance to resistance. So, depending on the value of the resistance and the capacitance and the frequency of the signature analyzer, you will get different signatures here. I'm going to do these for 60 cycles to begin with. Then we're going to go up to like 10 kilocycles and repeat the same measurements in a future video and see how much difference it makes in the signatures. Now, of course, the capacity and resistance won't change with frequency, but the capacity reactance will, of course. So all of that is to come in the next video in this series. I hope you will stay tuned for that. I hope you got something out of this one. And as I always say, I hope in the meantime you have a nice day.